Hello friends, greetings to you all from Anu Math Lessons. Hope you're all doing very well. In my previous video, I had applied the shooting method to solve linear second order boundary value problems. There were some subscribers who had requested for non-linear shooting method, meaning shooting method application for non-linear second order BVPs, which is certainly more challenging when compared to linear second order BVPs. So we are going to focus on slightly complicated topic today when compared to the shooting method application for linear BVPs. So this video, I have planned it in the following manner. We shall first understand what we mean by nonlinear second order BVP. Then we shall move on to revise what shooting method is, as we have already done it in our previous video. And then we shall work out a rule, a sequence of steps in order to solve these kind of problems and apply them there then into an example. So this would be the agenda that we would follow throughout this particular video. So let's quickly begin without wasting any more time. First of all, let us define what we mean by a nonlinear two-point boundary value problem. Now, a nonlinear two-point boundary value problem comprises of a differential equation of second order, wherein it's of the form y double dash is equal to f of xy y dash, where f of xy y dash is containing nonlinear terms. So what we mean by nonlinear terms is a product of the form y dash, or say y dash square, or simply even y square, or you say 1 minus y dash square, etc. These are some of the nonlinear terms. And if you have a differential equation of this form, where you say y double dash is equal to any of these kind of terms involved in it, then we call such an equation to have a nonlinear terms, or it is called a nonlinear differential equation. So a boundary value problem comprising of a nonlinear differential equation along with certain boundary conditions. This is as usual. A is one end and B is one end of the domain. So if we are having the boundary conditions specified at the 2 points, then these two comprise of a nonlinear BVP. So a nonlinear differential equation attached with two boundary conditions is said to be a nonlinear two-point boundary value problem. So explicitly, if we want to define f of xy y dash, let's take it of the form p of x y dash plus q of x y plus r of x, where any of these terms, even if one of these terms contains this nonlinear term, you call the differential equation to be nonlinear. So that's what we said all may not be linear. In that case, that particular differential equation along with the boundary conditions which we have specified above would be called the nonlinear two-point boundary value problem. So we are now interested in solving an equation of this type. So these are not as easy as the linear type, but requires a little more effort from our side. And that's where shooting method helps us. So let's now look into what shooting method is before we proceed with the ways of solving equations 1 and 2. As we have seen in the previous video, the basic principle of shooting method is to replace a boundary value problem by two initial value problems. But to do that, we have to first of all reduce the second order ordinary differential equation into two first order ODEs. And that is first done by making this substitution y equal to y1, so that dy dash becomes dy by dx, but y being y1, you substitute it here, so it's dy1 by dx, which I'll call it y2. Then we shall calculate y double dash, which is d square y by dx square. By definition, it's d by dx of dy by dx. But what is dy by dx? It is dy1 by dx. So I write that here. And d by dx of dy1 by dx is dy2 by dx. So y double dash is written as dy2 by dx, y dash is written as y2, and thus the second order differential equation which we earlier wrote as y double dash equal to p of x, y dash, etc., can now be split into two first order ODEs, where the first one will be dy1 by dx equal to y2, and the second one will be dy2 by dx, which is y double dash. According to the equation, it is p of x y2, y2 is nothing but y dash, plus q of x y1, y1 is nothing but y, plus r of x. And the boundary conditions remain as it is for now. So in this slide, what I have shown is the second order ODE is now reduced into two first order ODEs of the type 3 and 4. But we have to still rewrite the boundary conditions in terms of two initial conditions. Only then the problems become IVPs. Let's see that in our next slide. Let's rewrite the two first order ODEs that we have defined in our previous slide so that we can proceed further. So we have two first order ODEs that we have seen. That's fine, 3 and 4. And now let us look at what these boundary conditions imply. So let us plot these points in a two-dimensional system where I take the x and y axis, say this way, and A and B being 2 points on x-axis. And suppose I have some curve like this, that is, I have a point like this where I may take this point to be, what is my initial point here? y1 of a. y1 is y of a equal to alpha. So what's the value of y at a? So this is nothing but my a comma alpha. So this would be my alpha here. Similarly, b comma beta. So suppose I take this point. So y1 of b, at the other end, the value of y is beta. So this is b comma beta. Now, this is what is being given to us. So let me also drop the point there, and maybe this is my beta. And this is the b that we have here. So let me draw it this way. And this is a. That is your initial point. Now, if we want to convert this 3 and 4 and 5 into an IVP, what else we require is we require two initial conditions. Now, when I say initial conditions, they are those conditions which are defined at the initial point. So that means I need two conditions defined at x is equal to a. So I already have one condition, y1 of a is equal to alpha is already there. So what should I do now? I should find y dash of a also. Then in such a case, then I will have two conditions at x equal to a, which I shall use as y of a equal to alpha and y dash of a equal to whatever question mark it is after finding. I will have these two conditions. So I have two first order equations and two conditions defined at the initial point. So I have two initial conditions. My IVP is ready. But then, if I want to find out the value of y dash of a, what is the procedure? Instead of y dash of a, I know the value of y1 of b equal to beta. That is this point. This point is known. So what I need to do is from the point a comma alpha, I choose a slope. I'm sure everybody is aware that when I talk about y dash of a, it is talking about the slope at the point a. So we shall take a slope at at the point a comma alpha, call it y dash of a, say is equal to gamma 1. So I assume it to be gamma 1, and then I do the repetition, I do the entire problem. That's called in the shooting method language, I shoot by taking y dash of a is equal to gamma. I assume y of a equal to alpha as it is given. I take up y dash of a is equal to gamma as an assumption, and then I solve the entire IVP. That is 3, 4, and these two new equations if I call it to be 6. What happens in that case? I may end up in another particular case, I may end up some other curve. I may start it here. I may reach the point here at B. Exactly, I am not reaching at beta, but I may reach at a point beta 1. But what is the actual target? Please note the actual target, that is the y value at B, is beta. But by taking y1 of A to be gamma 1, where am I reaching? I am reaching the point beta 1. So instead of B, I am reaching beta 1, which is very far from beta. So that means the slope that I have chosen here is initially not correct. So instead, what I would do is take another slope, say y1 of A is equal to gamma 2, and again shoot it from this point and arrive at some other point here, say B comma beta 2. So again, I have arrived at a point beta 2, but I have not come anywhere closer to beta. And when it was a linear BVP, we said that we can shoot it 2 times, get 2 values, and use linear interpolation in order to get the final answer, get the final value of gamma. You could use what is called linear interpolation. This concept was used when you spoke about a linear BVP. But that possibility fails here as your point of beta 1 and beta 2 are very far and your differential equation here is nonlinear. But the initial procedure of developing IVPs is the same. So we choose two slopes. So what are the two slopes we have taken? Y dash of A is gamma 1 and the other is y dash of A is equal to gamma 2, and we have arrived at two solutions, say beta 1 and beta 2. Thereby, how to proceed, I will tell that in the next slide. But this is how we reduce that BVP into an IVP. So let's see what to do now. We said to convert this BVP into an IVP, we need to define y2 of A. What is that y2? I have suddenly called y dash of A. In our terminology, it is y2 of A. So it's the same. It is nothing but y dash of A, so that we arrive at the value. So how do we check whether the guess that we are making at y dash of A is correct? It is only by checking what is the value of y at B. If the value of y at B coincides with the target which is given to us as beta, we conclude that this guesswork that we have made for y dash of A or y2 of A is correct. So the check is the value of y at B is equal to beta. So suppose I choose the slope as gamma. Now I have not taken gamma 1, gamma 2, but I have chosen it as just gamma here in my theory. And in that case, that is y2 of A is gamma. Then what does the IVP consist of? It will consist of equations 3 and 4, and it will consist of the initial conditions y1 of A is equal to alpha and y2 of A equal to gamma. So solving this IVP. Now how do we solve this IVP? We said we are getting beta 1, we are getting beta 2. It's an IVP. We have methods like Euler's, Runge-Kutta method of the fourth order, Taylor's series. We could use any of these series in order to find out what is our beta 1 and beta 2. So in this slide, I restricted to this expression. So in this slide, what have we seen? We wanted to reduce the BVP into an IVP. We have done it. but by the choice of y dash of a by choosing it as gamma. But my goal is not to reduce it as one IVP, for which I will choose two values, gamma 1 and gamma 2. I shall explain that in my next slide. If we quickly revise what we did in our previous slide, we took up the curve where the end points of the curve was A alpha here, and here we took it as B beta, and we wanted to convert, and in the process of converting the BVP into an IVP, we had to make an assumption for y dash of A, say take it as gamma in general instead of gamma 1 and gamma 2, and then with that slope of y dash of A equal to gamma, shoot it from this point A comma alpha so that we arrive at some point called B comma beta 1. That is, what is beta 1 therefore? Beta 1 refers to the value of y or the value of y1 at B when the assumption that is made is gamma. So we could write it as beta 1 equal to y1 of B semicolon gamma. How do we read this as the value of y at B when the slope assumed is gamma. So we are arriving at beta. But what is the actual target? The target is beta. What have we arrived at? We have arrived at beta. Now beta 1. So if the distance, now here this is only a rough figure, but if the distance between beta 1 and beta is less than epsilon, now this epsilon is the precision that we require, the accuracy that we are looking for. So you could choose it to be less than 10 power minus 4 in general. Sometimes even you take it as 10 power minus 6. So if the gap between or the difference between the number that we achieved and the target given to us, that is beta, is less than 10 power minus 4, then the BVP that we are solving is completely solved. Our notion or the perfect, we have reduced it to an IVP, we are getting all the corresponding points in between A and B. So the problem is easy. But suppose the gap between, the distance between beta 1 and beta is not less than epsilon, then our aim here is to construct such a gamma in such a way that the gap between the beta that we find and the target beta should be as close as possible or within the permissible limit. The permissible limit is it should be less than 10 power minus 4. So now let us define what is the aim of our problem. Now the aim of our problem is to mainly find this gamma, which is a huge task. So let us see what to do. So we have now defined beta 1 as the value of y at B by choosing the slope as gamma. I'm sure now you agree. But what is the target? The target is beta. So suppose the difference between beta 1 and beta, that is the difference between y of b comma gamma, which is beta 1, and beta is less than epsilon, where epsilon is the desired accuracy or the precision that we require, which we have taken it as 10 power minus 4 in our case, then the BVP is solved. We conclude the BVP is solved. So what is the aim therefore of the problem now is to find that value of gamma in such a way that the difference between the y value at beta by using the new gamma minus beta, which is the target, is almost 0. I don't say equal to, but it is almost 0. So this is the aim. The aim is to find that particular value of gamma. So the entire problem of solving the 2-point nonlinear BVP now has reduced to the problem of finding the value of gamma in such a way that the choice that you are making, the value that you are achieving here by making the choice of y2 of A is equal to gamma should be the value that you're getting there is beta 1 and the target which you have is beta. That gap between the two is very, very close. It is in the permissible limit. So the whole problem has now boiled down to find the value of gamma. Now for that what we do is we define a function called phi of gamma, because we are talking about the difference and we want to minimize the difference. So we choose that phi of gamma as y of beta comma gamma minus b, y of b comma gamma minus beta. And now we will find out the roots of phi of y is equal to 0. It's a nonlinear equation, mind you, and we have a number of methods where which help us numerically to find out the roots of that particular equation. The main methods that we know are the secant method, the Newton-Raphson method. So the both of them are very highly applicable. Both the methods could be applied and can be used to find the roots of this equation, which are gamma. And the use of NR method. Now, out of the two methods, NR method, if you remember the algorithm, it deals with finding out the derivative of phi of gamma. As such, the problem is quite lengthy. So, finding out the derivative and then defining two slopes. As I told you earlier, we are not going to stick with one slope. We are going to find another slope, take another slope and do the problem. So taking up two slopes and then dealing with NR method becomes quite tedious. So instead of Newton-Raphson, though it is one of the famous and the most proven method, we apply the secant methods, wherein no differentiation of the term is required. Rather, only the choice of two initial slopes is needed in order to perform the secant method. So this slide is now giving us an exact meaning of what is the aim of solving a 2-point boundary value problem using shooting method. So our aim here is to properly choose the slope at the point A and shoot it in such a manner that we arrive at beta or very close to beta, which is where the gap is in the permissible limit. So the entire BVP problem is now restricted to finding out gamma. So what did we do now? We have defined that y of b comma gamma minus beta as phi of gamma, and our main job would be to find the roots of phi of gamma, wherein there are two methods of which we are going to apply the secant method, as Newton-Raphson method becomes slightly complicated as we require even a derivative. It's not that it is not possible, but it is certainly possible, but we are applying secant method in my video here. So let's now frame the working rule. Having understood this part, let's frame the working rule and then attempt the rule in a problem. Having understood from the previous slide that the procedure for solving this BVP of a nonlinear 2-point boundary value problem reduces to finding out the solution of this equation, that is to find out the right value of gamma, and the method that we are using is secant method. Let us now frame the working rule for the same. So the first step that we shall do is to choose two initial slopes. So as I told you, there could be some way, either a physical situation based on the problem to define it, or it is a mere guesswork of choosing the two slopes. That will be my first step of choosing the two slopes. Then I develop the two initial value problems. That is by taking the first slope gamma 1, I develop the first IVP, I call it IVP1, and choosing the second slope gamma 2, I call it to be IVP2. So I develop these two IVPs, and then I need to solve the two IVPs using any standard methods. So what happens when I choose y of b comma? So in the first case, I am choosing y of b comma gamma 1, and then the second one I will get the value of y of b comma gamma 2. So that's how I develop the two values. And how do I solve them is any standard method that I have mentioned. Now, what is the standard method that we are going to follow is the RK method. That's the one of the proven methods. And we are going to use the MATLAB code for RK method in order to find out what is the value of y of b comma gamma 1 and y of b comma gamma 2. So this will give me one beta 1 and this is another beta 2. So I solve this using the RK method. Then I calculate the value of phi of gamma 1. So what is phi of gamma 1? It's the value that we have found here first, minus beta, and similarly phi of gamma 2, the value that you have found, minus beta. So that gives me the error. Let's check whether they are very close and they are within the permissible limit. If not, what we need to do is refine. We need to refine gamma 1 and gamma 2. So we find that this is not less than epsilon, and if it is not so, that's when the secant algorithm or the secant method comes into picture. So we are now, let me recall, we are choosing the two slopes. Step 1, we are identifying the two IVPs. Step 2, we are solving the two IVPs. Please remember, we are repeating the process 2 times. RK method is used to get the solution for IVP1, which is y of b comma gamma 1. RK method is used for IVP2 to get the solution y of b comma gamma 2. Then we check it by subtracting with the target and we find that both are not less than epsilon, not within the permissible limit. So now we have to use the secant algorithm to refine gamma 1 and gamma 2. So what is the secant algorithm given by gamma n plus 1 equal to gamma n minus this particular term? Now, what are we going to do? We are now trying to define gamma 3. To get gamma 3, I need to put n is equal to 2 in it and in this expression, and that will be a refinement of gamma 1 and gamma 2. Now I have got a new gamma. So what is the new gamma? It is gamma 3. So go back and again define IVP3. So what does IVP3 mean? IVP3 is formed by taking the slope as gamma 3. IVP1 was chosen by taking slope gamma 1. IVP2 by choosing the slope gamma 2. I have refined gamma 1, gamma 2, found gamma 3, and now I frame IVP3 with the slope gamma 3, and I again solve by RK method and find out what is y of b comma gamma 3. So what is y of b comma gamma 3? Let's find out. And if that gap, if that difference with the from the target is less than epsilon, then I conclude that BVP is solved. If it is not so, we have to proceed with step 3. And now in this case, I have to find the refinement of gamma 2 and gamma 3 and then refine it and get me gamma 4 and then find out y of b comma gamma 4 using the same RK method. So naturally, once you see this particular procedure, you do find that it is not something which could be done manually. You need to definitely use a software tool to do this. But understand the procedure so that we could code it either in C or MATLAB or Mathematica and get the results instantaneously. It's easy to get. I have used the MATLAB tool. I shall be showing you the tool and the results by taking in a problem in the next slide. But let's quickly revise it. Step 1, choose the two slopes. Step 2, define the two IVPs based on the two slopes that you have chosen. Solve using the RK method to get two solutions. Compare the two solutions with the target. If both are not less than the required limit, then apply the secant algorithm to refine the two guesses we have made, and the new guess is gamma 3. Then use this to create IVP3 and again use the RK method to solve this IVP3 and that will give you y of b comma gamma 3. Subtract it from beta, check whether the difference is within the permissible limit. If done, then the BVP is solved, conclude your answer. If not, again refine gamma 2 and gamma 3 by using the secant algorithm and calculate gamma 4. Construct IVP4 and obtain y of b comma gamma 4. Once again, check it the gap between y of b comma gamma 4 with beta. If it is less than epsilon, BVP is solved, else the procedure continues again and again until we get a value which is very close to beta or which is in the permissible limit. So this is the procedure. Sounds easy because we are doing it using just not a manual one. We are going to use a code. So I'm sure using the code things will become easy. If you have to do it manually, yes, it's a huge task because the equation is nonlinear. We have no other option. But since we have taken up the code, I will show it to you. The things become very easy. All these steps we shall exactly follow in the problem which follows in my next slide. Let's start with the problem now. The problem reads, solve y double dash is equal to xy square. So you see it's a nonlinear equation. With boundary conditions, y of 0 is 1 and y of 1 equal to 2, and the h value that is given to us is zero point 0.2. So let's see how to solve this. So we are given here that 0 to 1. So we have the points from 0 and here it's at 1. It's 0.2. So I divide or discretize it. So it's 0.2, 0.4, 0.6, 0.8 and 1. And at 0, you know the value is 1 here. And at 1, you know the value is 2. So actually our aim is to find out the values at each of these by converting this BVP into an IVP first. And since you have a nonlinear one and we are using the shooting technique, let us see how to do. But before we proceed with the slopes, we have to first talk about the reduction of the second order ODE into a two first order ODEs. We shall do that first and that shall be shown in this slide. So as we explained in our theory, we choose y equal to y1 so that y dash will be equal to y2, y double dash is equal to x y dy2 by dx, which is nothing but xy square, or y can be written as y1 square. And now simplifying or rewriting, now the second order ODE is now written as two first order ODEs. The first one becoming dy1 by dx equal to y2 and the second one being dy2 by dx equal to xy1 square. So the boundary conditions have not been touched so far. Now this only the two second order ODE is now reduced to two first order ODEs in this particular slide. Now let's move on to the next step in the next slide. Let us now continue. Our problem is to reduce the BVP into two IVPs. So as we recall, the domain of our problem is 0 to 1 and the H value is 0.2. So we are now interested in finding out the value of y at 1 by choosing the value of the slope at 0. So the aim of the problem now has reduced to finding out the value of gamma, which is the choice of y2 of 0, and so that the value of y1 at 1 is almost close to beta, and beta value that we have given here is 2. So let us check and let us see what kind of choice we can make. So the aim of the problem here, therefore, is to find out the value of gamma in such a manner that phi of gamma, which we define as y of 1 comma gamma, which means the value of y at 1 by choosing the slope as gamma minus the target, which is beta, is almost 0. Beta in our case is 2. So that's where I said that we have to check with 2, subtract it from 2, and check whether the value is close to 0. So this is our motive for which we have to make the first choice. We have made the first choice by choosing the slope at 0 to be 0.5. Now, on what basis did we choose this? I openly tell you, it's completely random. There is no physical situation that we have here. So we have chosen it at random, and then we have now constructed the IVP. So now, because I have defined y2 of 0, another initial condition for this problem, IVP1 becomes the first equation, the second equation, and the two initial conditions. Now this condition is already given. This condition is given, and this condition is assumed now. It's assumed by us. So this together forms IVP1. And this IVP1, as I told you in my previous slide, that we would be using the Runge-Kutta method in order to solve this using MATLAB. So the next slide shows the code that I have used to solve this IVP and the corresponding solution that we get, and also we check whether it's close to the beta value or not. Let's see the code now. As you can see now, this is the code that I have developed, and the value that we have, the values that we say is h value here is 0.2, x value, the initial value is 0, the final value is 1, y1 initial value, that is y of 0 is 1, that is given to us, and the value of y2, meaning the value of y dash, the value of y dash at 0 is assumed to be now 0.5, and that is what is written here. And we have used the RK method algorithm in this particular section, and we have run the program, and to see that the final values of y, the final value, this is at, when I put here 0, this is at x equal to 0.2, x equal to 0.4, x equal to 0.6, x equal to 0.8, and x equal to 1. So at x is, these are the x values, and these are the y values, and these are the y dash values, which we have called it as y1 and y2. So we see that by taking y dash of 0 equal to 0.5, what have we arrived at? The y value at 1 is 1.7852. As even the picture says so, the graph also says so, that at x equal to 0, from here, if you see this, let me mention it here, at x equal to 0, the value of y is 1. Correct? This blue line. And then when at x equal to 1, the value is 1.7852. So I have used the code in order to develop the solution of this IVP1, and we see that here that the value of y by taking your gamma value as zero point 0.5 is 1.7852. Now let us check what is the actual value. The actual value, what is your actual beta? It is 2. So what will be the difference between the two? 1.7852 minus 2 is certainly not very close, and it is not less than epsilon, and therefore let us move in for the second choice by choosing another gamma value. Again, it is a guesswork, as I said, but the procedure is exactly the same. As the first choice did not give us any closer value to the number 2, we shall choose another solution, another for the slope, which is here I have taken it to be 0 0.8. Now, what is the IVP? Equation 1, equation 2, y1 of 0, which is given to us. This is given, and we have assumed now the slope at 0, which is 0 0.8. Let us again proceed by using the RK method. Let me show you the code and the solution that we get automatically. Let us look at the code that we have written, similar to the previous one. If you note here again, h value is 0.2, initial value of x is 0, final value of x is 1, the y value at 0 is given to be 1, and this is y dash of 0, which is the guesswork that you have done. It's simply, now you have chosen it to be zero point 0.8. So you see what happens when you're choosing zero point 0.8. What are your x values? The x values here that you can have are 0, zero point 0.2, zero point 0.4, zero point 0.6, zero point 0.8, and 1. And this y1 means y, y2 means y dash. We are interested in y value at 1. And what are you getting? You're getting the value at 1 to be 2.16. So it's already crossed 2. So the value is 2.1639, as you can also see in the graph here. So this is the MATLAB code for the IVP2, and now we have found the solution is 2.1639 by choosing the slope as zero point 0.2. And again, if you see the difference from 2, it is nowhere in the permissible limit. Now your gamma 1, which you chose as zero point 0.5, gamma 2, which you chose as zero point 0.8, where your phi of gamma 1 and phi of gamma 2 are not less than epsilon, and so both need a refinement, and that's when we obtain gamma 3 using the secant algorithm. I will show that in my next slide. As we saw that gamma 1 and gamma 2 did not yield answers, we now need to proceed to the secant algorithm. So let's quickly revise what did we do in the previous two slides. We took gamma 1 as zero point 0.5, so that the solution that we got was 1.7852. Phi of gamma 1, which is the difference of y of 1 minus 2, that gave me this value. This was my first choice. The second choice we took as zero point 0.8. Proceeding in the similar manner, got the result for y at 1 to be 2.1639, and when we took the difference, it is 0.1639. So we have got both the values, both were not close, and therefore a refinement is needed, as we discussed earlier. So we have now written the secant algorithm. We want the refinement of gamma 1 and gamma 2. So I need to find the value of gamma 3. So I put the value n is equal to 2 in this algorithm, and see what happens. I get gamma 3 in terms of gamma 2, gamma 1, phi of gamma 2, phi of gamma 1. I have all the values here. I substitute them in this particular formula and get the new value of gamma 3. Now what is my next step? So this is the refinement. This is the refinement of gamma 1 and gamma 2. I need to go back and now write IVP3 and once again solve it using my RK method. Having got the refined slope as gamma 3, which is equal to 0.6702 from the previous slide, let me now construct IVP3. So what does IVP3 give you? The equations and the initial condition and the slope at 0. And now again we shall go back to RK method in order to solve it and check whether at least this result gives us a closer value to beta. Let's see. Let's see the code for this IVP3. So again, h is 0.2, initial value of x is 0, 1, y of 0 is 1, and look at this. This is gamma 3. This is y dash of, or y2 of 0 is equal to 0.6702, which is your gamma 3. This is the refinement. And what do we get here? Look at the values again. For x, we have 0, 0 0.2, 0 0.4, 0 0.6, 0 0.8, and 1. And these are your y values. These are your y dash values. We are looking at the value of y. Now, what do you find here? The value that you've got is 1.9987. So it's almost close to 2. So we have refined gamma, and we have now brought it to a point where it is not exactly 2. And is it also in the permissible limit? Let's check. Still not, because we said the permissible limit is 10 to the power minus 4. So let's still try to make it closer. So what do we do further? Again refine, but refine which two gammas? Now gamma 2 and gamma 3 are to be refined and to generate what is gamma 4. So I hope the application of RK method becomes very easy once the coding is done. We just have to go on replacing the slope value so that the results are obtained immediately one after the other. So let's see what is the refinement and let's see if we are arriving at beta or else should we still go to gamma 5. So by proceeding with gamma 2 and gamma 3, we have still not obtained and therefore we have to go in for a refinement. Let's write once again what did we find? This is gamma, my second choice. This is the difference that I get. And then gamma 3 was my refinement of gamma 1 and gamma 2 and I get this as the difference. Now let us use the secant formula again, but I am looking at the refinement of gamma 2 and gamma 3 to get gamma 4. So I put n equal to 3 in this particular algorithm and let's see how it turns out to be. It is this. All the values are available here. So I substitute them, I simplify and I get the result to be not very big difference. It is 0.001. That is the difference that I have. So gamma 4 is a new refinement value. Now with this gamma 4, let us construct IVP4 and then let us try to solve the IVP using RK method. Hopefully this should give us the answer. Let's see. Let us now look at the coding. Again, we have h.2, x value 0 to 1, initial is 1, and this is our new value. Y dash of 0 is 0.6712, and if you look at the solution, x values are 0, 0, 0.2, 0.4, 0.6, 0.8, and 1. And at 1, what do you see the value is? 1.9999, and that's almost equal to 2 and it is satisfying because we don't take it further. You could also take 0.6713 and also try it, the difference would be similar, and therefore we have achieved with our result by saying that the respective gamma value that we are choosing is 0.6712. So we have completed the problem. Now the time comes how to conclude our answer. We have taken the step size of x from 0 to 1 in steps of 0.2. So let us show the conclusion for each of these values in my next slide. So I hope you understand this particular structure, and this comes by practice. It is not very tough. Once the one code is created, the others are only obtained, the results are obtained by merely changing the respective values and getting the answers consecutively. Let's see our conclusion in my next slide. Now let's declare the result in the form of a table giving the values of x, y, and y dash at every point between 0 to 1 by taking the step size as 0.2. So I draw a table like this. So the x values start from 0, 0, 0.2, 0.4, 0.6, 0.8, 0.9. zero point nine. The value at 0 is 1 is given. The value at 1 is 1.9999. This is, we are not taking it as 2, mind you. We are taking it as this, which is very approximately equal to 2. How did we get this result? By making a choice. So this was our gamma value. Gamma value was 0.6712. So we created y dash of x, and based on that we got, because of this gamma value, we got y of 1 comma gamma 4. Actually it was not exactly gamma, as 1.9999. So I'm not referring it to 2 as it is given in my problem, but for me 1.9999 is equivalent to 2. So let us replace it only by this number. All these results are obtained from the program that we wrote. As you see, all these values are from that particular program. The final program that we wrote, the values are obtained from it. Kindly note, I repeat, y of 0 is 1 is given. Y of 1 is 1.9999. Actually, problem says 2, but we are concluding the result with this by assuming that y dash of x is 0.6712. So you look at it, we have used secant method, Runge-Kutta method so many times, and we have obtained the values at every point in the domain that was asked. So the beautiful kind of a technique it is, but it is surely time taking to understand and to implement. But once you understand the concept, coding is something which nowadays everybody is doing, and even these codes are available on the internet. So you could either write a simple C program or a MATLAB like I did, and you could check it with any of your results. So you could attempt this particular part by choosing any nonlinear BVP and attempting this working rule. If you follow this working rule, things become very easy. So if you have a structured way of doing it, I have tried my best to convince and give you the concepts correctly. I hope you try, and if you have any doubts, please feel free to post it in the comment box. To the best of my knowledge, I shall clear your doubts. And it was very nice that you came forward asking me for bringing out new videos. So this was one such where I took attempts, and my research also is completely using shooting method relating to partial differential equations. So that's even more tougher and highly non-linear. So shooting method is certainly one of the most important tools, but there are plenty of them too. But shooting method is one of the basic techniques. We have now shown it for ODEs. I shall slowly extend this for even solving simple PDEs also in my subsequent videos. I hope you like the video and I hope you benefit out of it. Kindly watch it in full and give me your fresh and free comments. Thank you. God bless. Goodbye.